Good morning. It's time to start our last session for the week. So today we have the student elective tutorial given by Robert Allen, and I would like to invite the students to introduce themselves and the speaker.
Good morning. My name is Mei Yun Lin. I'm a fifth-year grade school student at University of Illinois Urbana-Champaign. Today, I'm here to introduce Dr. Robert Allen. Dr. Robert Allen is a senior professional staff at Johns Hopkins University Applied Physics Lab. His research is to investigate energetic ion population and electromagnetic ion cyclotron waves at the magnetosphere of Earth, Jupiter, Venus, and Saturn, as well as studying stream interaction regions with S, Parker Solar Probe, Solar Orbiter, and Stereo. Prior to joining the Applied Physics Lab, Dr. Allen obtained his bachelor degree of physics from University of Texas Arlington in 2011, and a PhD degree of physics from University of Texas San Antonio in 2017. In 2016 to 17, Dr. Allen was elected as the GEM student rep. Currently, he is the instrument scientist for the Superthermal Ion Spectrograph Sensor on Solar Orbiter and a member of Parker Solar Probe Project Science Team, and was awarded the NASA Silver Achievement Medal as part of the Parker Solar Probe team. Today, Dr. Allen is here to give the talk of heliospherics missions and instrumentation, past progresses towards future implementation. Please welcome Dr. Allen.
Awesome, thank you. All right, so first I'd like to thank the student reps for the invitation to give this talk and also for the nice kind of broad topic that I get to talk about. So it gives me a lot of freedoms to have fun. And so with this, what we're gonna be talking about is kind of heliophysics missions and instrumentation in general.
Sorry. Oh my God. Sorry. Just to take it off. So. Can I hide that thing? Okay.
Thank you. And really it's kind of giving my perspective of where we're gonna be going to in the future. And part of this is also a drive so that, you know, for those students out there that are doing work more on the modeling side is also kind of give an idea of where we might be going with future mission implementations. So to start off with, I wanna have a disclaimer. So I am not going to do an attempt to summarize every mission that's ever flown or currently in space or every concept that exists. That would simply take way too long and I will inevitably leave something off. So someone will be mad at me. So apologies if I don't talk about your favorite mission. There are so many fantastic missions that have flown or are currently flying. And so everyone has done a great job at that. But also this is probably just going to really reveal the bias in my own studies and what I focus on myself and what missions I really like. And so with that, grain of salt there. But also this is going to be my perspective. And so if we're ever thinking about the future direction of the field or future direction of missions and where we stand, this is not going to be a complete picture. And so I encourage everyone to be talking to everyone else to try to really find out kind of your interpretation of where we should be going. So even though there's been a lot of work in space physics prior to the space age, whether it be through, you know, looking at chronograph images or looking at ionospheric sounding, for this talk, I'm mainly focused on space-based missions. And so I'm going to start with Sputnik 1, which was the first artificial satellite. And even with this very first mission, we were able to do a lot of interesting science. So we could actually do you look at the density of the upper atmosphere being deduced from the drag on the orbit, we're able to get information on the ionosphere from propagation of the signals from Sputnik. Actually, it's a really fun fact for me being from APL. In an attempt to better triangulate where Sputnik was, we realized at APL we could invert that and develop something like GPS. And so there was a lot of really great innovations that came out of this very first space-based mission. Of course, with this being a Soviet mission, America was not to be outdone. And so we very quickly the next year followed up with our own artificial satellite, which was Explorer 1. And this included a cosmic ray detector that was basically a Geiger counter that was able to look at the energetic particle populations in Earth's space environment. And from this, though, it led to Van Allen hypothesizing the existence of a radiation belt because he hypothesized that his instrument actually saturated. And that wasn't confirmed until slightly later with Explorer 3. And so already with these very early on missions, we were starting to really paint out the environment around the Earth. So the year after that, we had Luna 1, which I include as another major first. This is the first spacecraft to go in interplanetary space, not by intention. It was intended to impact the moon, but the second stage of the rocket didn't quite go according to plan, and so it missed the moon. But what this allowed is for it to take this whole host of instrumentation for science and both do a near lunar flyby and deduce that the moon probably did not have the same kind of dipole field as the Earth does, but also then go out into the solar wind to make measurements there for the first time. And then a few years later, we had Mariner 2, which was the first spacecraft to successfully conduct a planetary encounter at Venus. And so already in these very first few years, we're able to accomplish quite a lot in this new space age. So now going into the future a little bit more and much faster to get more to current times. In the 70s, we had the Voyager missions. And so Voyager 1 and 2 visited the gas giants. Voyager 2 then was able to go to the ice giants to take the first measurements there. And so these were also now the first spacecraft to get in situ measurements in interstellar space. And so kind of being able to push that envelope further. We also had the AMTI mission in 1984, which was a really exciting mission because it was an international collaboration. It was a mission that had 3 spacecraft. So we had AMTI CCE from the US, AMTI UKS from the UK, and AMTI IRM from Germany. And this also included active experiments where they had kind of capsules they could release gases into space and kind of watch for that diffused out and do these more active experiments. And so again, this is starting to kind of find new ways to explore our system, but also push the boundaries of our knowledge with these firsts. After that, in the 90s, we had Ulysses. And this was a really exciting mission because it actually used a Jupiter flyby to get out of the ecliptic plane that all the planets are in and actually do these latitudinal scans of the solar wind and really kind of end up having some paradigm shifting knowledge of, throughout the solar cycle, how the sun is structured and how that imprints itself on the more global heliosphere. And then there was the Cassini mission in 1997, which had an extensive tour of the Saturn system, visiting the moons and the rings, and was the first spacecraft to go into orbit around Saturn. And some of the really cool things with that is, it got kind of able to kind of start indicating that there was actually like a liquid ocean on Europa because of the induced magnetic fields it had. And as well as having such a long-lived mission, you're able to actually start looking at seasonal impacts in that system. And so again, kind of with all of that, we're really pushing the boundaries. And so with all of this, this now brings us to where we are today, where we have many, many missions, many data sets, whether you want to look at the lower ionosphere thermosphere system, going out to the inner magnetosphere and outer magnetosphere, and then even leaving the magnetosphere as you go further out. We know we have observatories at L1 to get upstream information. And then beyond that, in the inner heliosphere, we have missions like Solar Orbiter, Parker Solar Probe, and Still Stereo A to kind of paint out that picture of the inner heliosphere. And then even beyond that, we still have the Voyager missions and we have New Horizons. And so we're at this point where we really do have a large number of assets out in space taking great data sets and that we can use for all of our science investigations. And so with that, to kind of go into a very NASA-centric viewpoint for a second, that allows us to paint out our heliocentric system observatory. And so this is a graphic from NASA that really shows all of the current operating missions in development that we have. And you see that it really spans a very wide range of different kind of subdomains within space physics. And so with that, I think it raises the question of, okay, so where do we go from here? Because at this point, we've had all of these firsts. If you want to ask, have we ever measured a certain quantity like the magnetic field at a certain location, the answer is probably yes. That measurement has been taken at some point in time. And so we have these really broad shoulders and this really great foundation to stand on when we want to look forward. And so I know that, there's been times in the community where people have kind of been a bit terrified by that, of the fact that we do have all these, all of these main first discoveries have been made. But really, from my standpoint, it really sets us on a really great framework to ask now the more deeper questions of, now that we have these observations, how can we construct missions and really tailor what we want to go after to specific scientific questions with that knowledge. And so the first thing I want to talk about is constellations then, of how do we then take multiple data sets from multiple locations, and instead of having a single point measurement framework in our head, how do we kind of build out a better picture and do better science with having more of a spatial or temporal coverage? But before doing that, I want to go back to the HSO. And the reason is that, before talking about any kind of future implementation, we need to recognize that there's still a lot we can do with what we currently have. And so with that, I do think the HSO is still an under-tapped resource. I think that we are at this point where we have so many missions, and yet too many times you see papers that are focused just on one mission or one asset, when it could be benefited from this more global perspective. And one really great example of that is a paper by Mark Engelbretson from 2018, where he wanted to look at EMIC waves during a strong compression of the day 7 neopause to see what effect that might have on EMIC waves. And in his study, he was able to use observations from MMS, RBSP, GOES in a series of ground-based observatories, and really then look at, over a large swath of space within the magnetosphere, when you have these compressions, what is the spatial coverage of that generation region exciting these waves? How do the properties of these waves vary by location? If you're closer to the neopause, do you see more alpha band EMIC waves, whereas when you're further in the magnetosphere, those go away? And so with kind of combining these different assets, he's able to get a deeper understanding of EMIC waves in the magnetosphere during these times of sudden compressions. And if you're wondering, is there a home for these kinds of studies? The answer is yes. There's actually the whole Heliosphere and Planetary Actions Group, which is an international initiative focused around this solar minimum we're leaving right now, but really trying to aim at using the HSO to get this interconnected sun, heliosphere, planetary system framework. And so currently, to kind of continue the trend we've had in plenary talks all week, there is a special issue for that. So for those who might be having a study utilizing the HSO to kind of understand this more broad impacts and system science level view, we currently do have a special issue in a number of AGU journals. So you can kind of pick your favorite and go from there. And we have an extended deadline for those until the end of October. So if you're working on a study, please consider that. But one thing I want to go into is, of course, there are limitations to the HSO, which is why we always do push for new missions. One limitation is that typically different missions will not intercalibrate with one another on a very frequent basis. And so if you want to apply techniques where you're actually doing a straight up, this density divided by this density, you need to apply a slight grain of salt and actually get to know each individual instrument and its caveats. Additionally, missions typically are not going to be situated on the relevant kind of scale you want to look at or the positions you want. And so you really start relying on these fortuitous conjunctions. So if you have a really strong storm and you want to look at how the atmospheric plume kind of evolves and stretches out, there might be no spacecraft there. You don't really know, and none of these orbits really optimize together to get you that coverage. But you should always look. You might look out and you might have a really great study because of that. Additionally, missions don't carry identical payloads. And so you need to kind of ask yourself, what do you need for your science? If you need really high mass resolution, then you need to understand that some instruments or some missions really going to carry total ion measurements. And maybe you can use that, and maybe you can't. But because they're not equally instrumented, it will kind of whittle down a little bit of what your options are going to be. Additionally, spacecraft tend to operate based on their own science priorities. And because of that, just because a spacecraft might be at a really ideal location for you, doesn't mean it's collecting data. We have had instances, for example, when Solar Orbiter and Parker Solar Probe were really great alignments, and one of them decided to do a spacecraft software update during that time period, so you have no data. And so because of this, there's really no necessarily large mandated coordination to make sure that things are done in a way that's not going to impact your science. And so to overcome all of these, the obvious answer is that dedicated constellation missions can be used, where you can put spacecraft with the right instrumentation in the right location with the right separation on orbits that will optimize your coverage for your science. And so at times, then we need to start thinking, if our science pushes us to the point where the current HSO is not going to be sufficient, then what can we do about that? And so for that, I kind of want to break up constellations into two different categories. So I have this kind of small n or small number constellations. These are when we have kind of, 6 or less spacecraft. And then I'll later on get to large n constellations. So when you're talking about having 30 or more spacecraft within a constellation. And really, I want to break these up because they carry different considerations to have, and they do actually fill different niche roles within our science. So some advantages for these kind of small n constellations is you have the ability to get higher order variations in a system over just one spacecraft. And so whether you want to look at something that has a Gaussian distribution or a sigmoidal distribution, if you only have one measurement, then you have one value, and that's not going to be representative of that variation. When you start getting to two spacecraft, you have a spatial gradient. And if you have two spacecraft that are close to one another flying through the same region, you can kind of start disentangling spatial temporal variabilities. And kind of as you go up in number of spacecraft, you'll see you quickly gain the ability to start constraining these systems. And so with that, a lot can be done with a limited number of spacecraft if you have the right question. You also then gain the ability to use much more powerful techniques in your data analysis. And so I do direct, especially all the students, but really everyone, to the series of ISI books that have come out on multi-spacecraft techniques. Whether it's some of the ones that originally were written back in the cluster days and then revisited later on, or the new one from 2020 on ionospheric multi-spacecraft analysis tools. And so these have a whole host of different techniques you can apply if you have multiple spacecraft and you want to really get to the higher order physics that exists. Another advantage for having a limited number of spacecraft is that it means that you can probably get by with a single launch. And while that might sound really particular, it's useful for a number of reasons. First off, it does reduce cost, which is always a good thing. But the second thing is if you want to put these spacecraft near each other, if you start going to multiple launches, you need to find ways to ensure they end up kind of having that rendezvous in space. And so a single launch is really easy if you want to then have them be close together. And this has been done before with THEMIS and MMS as well as cluster. And future mission concepts that are currently being developed are also trying to use this kind of single launch manifest idea. But as with everything, we do have some considerations that we need to kind of keep in mind. When you are talking about small number of constellations, while you kind of unravel previously elusive variability dynamics and system level timing of events, they're still going to be targeted to particular region and scale size. And so, if you wanted to have more of a global system level viewpoint, you're not really going to be able to gain that in any kind of single time snapshot. And so, for example, if you think of MMS and cluster as they originally envisioned when they're in their tetrahedron, you're able to get at these electron and ion scale dynamics, which is really critical for our fundamental understanding, but it's at a particular location. So while you might be able to go through the EDR and take really good measurements of what's going on in that electron diffusion region, you're not necessarily going to be able to have any idea of what's the extent of that X line. And so it does carry with it some constraints. Just like that, THEMIS as it was originally envisioned, so we can actually get these nice radial profiles of the tail and look at the timing of bursty bulk flows and try to get where the substorms are being generated. For all of that, it is still a single line you're getting. And so you're not necessarily painting out any kind of dawn-dusk asymmetries for a single event. Now, statistically, you can go through and try to build that out. And so it's really great then for this targeted science where you have these questions and you recognize that you would like to have a lot of instrumentation for those. Because it then kind of really enables a lot of that, but you do understand then you're not going to get this global coverage. And this is also the point where now cross-calibration becomes important. So especially for MMS, if you want to be looking at these very small variabilities on very small spatial scales and small variabilities, if your instruments aren't intercalibrated very well, then you don't really know if what you're measuring is a signal or noise. And so kind of going forward from there, there are a few concepts that have been coming out that are being proposed for the future that utilize a small number of spacecraft techniques. And so one of them is the Magnetosphere Ionosphere Observatory NEO concept that Joe Borowski has been putting forth. And it's really trying to connect the localized magnetotale dynamics to ionospheric impacts. And so what this concept would do is you'd have one main spacecraft, which is really exciting because it has a relativistic electron accelerator that would fire a beam of electrons along the field line and the loss cone at the Earth. And so if you ever want to like fire an electron gun at the Earth, this is the mission for you. But then around that main spacecraft, you have these auxiliary smaller spacecraft about 100 kilometers away to look at the local gradients. And so you're able to then get information on, okay, well, we know from firing that electron beam into the ionosphere and using a ground-based system of all sky imagers, we know where we're spatially connected to in the ionosphere. And so then if we see certain structures in the aurora near where that foot point is, and we look at the local gradients around that main spacecraft, it gives us that ability to start drawing some of these connections and start figuring out some of these generators and drivers of different phenomena. But again, it's doing all of this great science with a limited number of spacecraft. There's also, if you want to start looking at more magnetotail dynamics, if you want to know how and why magnetotail energy transport is localized across the tail and how does this localization affect particle acceleration by transients, this is also a problem that intrinsically you just can't do with only a single point measurement. You need to have multi. And so there's the wedge concept that's being put forth by Kevin Genestretti, which would be a multi-point crosstail set of spacecraft with separations of several RE located about 15 to 50 RE down tail. And so this would allow them to starting to detangle, you know, which of these scenarios of tail dynamics really is the one taking place. This is also useful for solar wind studies. So to be shamelessly self-plugged for my own concept, if you want to start learning about solar wind mesoscale dynamics and how those might affect the Earth system, and just generally how the solar wind is structured to begin with, this is another problem where you do need these multi-point measurements at the right separations. And so the intermeso concept would use 4 spacecraft at near 1 AU in an Earth trailing orbit. It's kind of falling behind the Earth in its orbit, and they slowly separate. And so early on in the mission, you have them all close together, looking at the lower end of the mesoscale solar wind. And as the mission goes on, they separate out so you can start kind of spanning through this range, which is really important for this mission because we know that different solar wind structures have different intrinsic scale sizes you want to look at. And so this way, with a limited number of spacecraft, or 4, you're able to actually span that entire range of science without needing to go to something more massive. And so then that brings me to the large number of constellations. This is when you want to kind of say, okay, well, sometimes it's really great to have 4 or 5 spacecraft. But what if you want to talk about something that's, you know, 30, 40 or more? What can that really enable for us? And so really, you know, this is where it does enable this global coverage across multiple scales. So if you want to think about the magnetosphere system as having all this mesoscale variability within the system and being very dynamic, then as you would imagine from seeing the different movies we get from different simulations, you really can't get by with only a limited number of spacecraft. You do need something a bit more robust. And so with that, this would allow you to then not only get this kind of global coverage and look for these mesoscale variabilities, but it also allows you to fan them out and look within different subdomains of the magnetosphere to really see on a system level, how do each of these subsystems impact the next subsystem? And then if you can even think of constellations that are so massive that you're spanning, you know, solar wind to outer magnetosphere to inner magnetosphere and really try to tie everything together. This also allows even more advanced techniques. So you can do more advanced tomography and higher order spatial temporal reconstructions because you have so many measurements. But of course, you have a lot of considerations. If you want to amp everything up to have a large number of spacecraft, this poses a data visualization challenge. We all really know and love all of our time series stack plots. We love to order everything by time and just have all of the panels. But if you think about it, if you have 70 spacecraft and they're all located at different parts of the magnetosphere, that's not going to tell you anything. You know, you might see bumps and wiggles at different points in time, but what if that's temporal? What if that's spatial? You can't really reconstruct anything that way. And it just would be too much for your brain to really digest that. And so from that, you know, we have to start rethinking how do we want to show our data if we want to have large number of spacecraft. Additionally, cross-calibration becomes very challenging. We've gotten really good at doing cross-calibration among a small number of spacecraft, but if you are talking about something like greater than 30 spacecraft, that's an entirely different beast. And you know, we need to work on our own framework of how we're going to actually keep all of that intercalibrated, because a lot of the AI ML calibration techniques that have been kind of put forward and sometimes used to aid researchers, none of those have really demonstrated themselves to be robust enough where you could just totally trust that to run in the background unaided. And so we really do need to find a way to, you know, if we want to push our architecture to this point, we need the infrastructure at the back end for the intercalibration. Additionally, when you start talking about, how many launches do you want, you kind of have multiple options. So if you wanted to still push for a single launch, everyone can think of things like Starlink, where you can put a whole bunch of spacecraft up there, but that means they're really tiny. And so then that really limits what you can put on that spacecraft if it is so small. The other option would be to slowly build this out. So you could do things like ride shares and kind of every few launches try to add to your constellation. But then that runs into the issue of launch availability. Because even today, we do have missions that have been selected to go forward and are having issues finding the launch vehicle for them from the rideshare approach. And so with that, then they're also typically going to be more expensive because you just have more spacecraft. And so this can be mitigated, such as limiting your instrumentation. Do you really need that Rolls Royce of instrumentation that we all know and love? Or can you get by with only having magnetometers or some limited plasma sensors? We can push for miniaturization to fit on smaller buses, and we can go with commercial off-the-shelf parts. So things you can just buy from a commercial vendor, which can be much cheaper. But especially for that last part, that has more considerations for it. If we do want to go this route of miniaturization and COTS, this really can be a game changer for us. It can be potentially cheaper, which allows us to push for these larger number of spacecraft missions. It could also make it where a mission is cheap enough that if you want to get to certain parts of the atmosphere, we're going to have a lot more drag, that previously it was just prohibitively expensive to have a mission that might only have a month lifetime. This might be able to push us to the point where it's inexpensive enough that we really can probe those atmospheric depths. And we're actually going this way now as far as embracing COTS. So on the upcoming PRISM Lunar Vertex mission, they're going to have COTS magnetometers. And so in this, they're already starting to find ways to utilize these to be an enabling force for us to move forward. But of course, nothing is free. And so you're going to have some trade-offs. So in this case, typically when you start going, especially to COTS parts, you're going to be talking about, reduced performance, whether that's going to be increased noise and background levels, of course, the resolution, limited dynamic range, limited reliability space applications, because they're not all going to have the same rad hardness. You can also have maybe some more thermal variations through them. So there is more to consider. And so for some science questions, it's okay to have that trade-off. It's okay to have a not as great measurement, but to have a lot more of them. In other applications, that might not be a trade-off that you really can put up with. That means you really do need that better measurement. And so this is something that I think us as a field need to kind of work to find, where does it make sense to have this have a home in our architectures, and where do we still need the more traditional science grade instrumentation? So that being said, we do actually have an example of a large N constellation mission, and that would be the Ampere data set. For those that don't know, Ampere is made up of taking data from the over 66 active Iridium spacecraft that form the satellite phone network. And what the Iridium Corporation had done at one point in time was go through and do that minimization problem of if they want it where you could have one of their phones and be able to reach a satellite from anywhere in the world, what is the fewest number of spacecraft you can do to have that? That's what makes it commercially viable. And so they did that problem, came up with 66, and they do have some reserve spacecraft in case something goes down. And through an NSF collaboration, the Ampere team was able to get access to some onboard magnetometers that originally were there for attitude control. And so these are not science grade magnetometers. They were not intended for any of these uses. But from that, after a tremendous amount of effort from the Ampere team, they were able to clean up that data set enough, do inversions, and start building out actually nice field line current system maps, where you have this now global coverage. So you have both hemispheres of the field line current system. And so this is a great example because it really does highlight all those considerations I had before. You don't see 66 time series. You see this nice spatial plot showing all the variations that each of the spacecraft sees. And then that gets converted into nice contours of the field line current system itself. You're not flying necessarily science grade parts. You have avionics mags, and you don't have a full suite of instruments. You have avionics mags. So it's one of those where if you do whittle things down enough, then you really can reach these large numbers, and it can be really enabling and really powerful for the community. But you have to understand what you're giving up at the same time. So as far as future concepts for this, there are a few. So one of them is Magnetosphere Constellation, or MagCon, that seeks to determine how the magnetosphere processes, stores, and releases energy from the solar magnetosphere interactions. And so this is a concept that's been around for quite some time now. It's kind of gone through a few iterations every decadal or so. And so the current iteration as it stands is 36 spacecraft put into 3 string of pearls orbits. So you have 12 spacecrafts per that spatially span from about 5 to 18 RE radially. And the inter-spacecraft separation at apogees less than 1 RE. And so that really enables you to start pulling out some of these mesoscale dynamics that we expect to have in the magnetosphere and really start looking at how this system responds to the solar wind. And this is a concept that currently Larry Kepko has an HNCS looking at. There's also the pilot concepts. This is the plasma imaging local tomography experiment that David Malaspina has been working on. And this is actually a really neat concept. So they use 30 identical microsats that are their kind of radio sats and 4 small satellites that are their plasma sats. And so what they really want to go at is really looking at the mass and energy flow within the inner magnetosphere. And from that, using tomography from those radio sats, they're actually able to pull out the really cold plasma densities and really look at how that's structured and look at the atmospheric escape and outflow. And so this is a really fantastic concept that is, definitely using a large number of spacecraft in a really interesting and unique way that I've not really seen before, that really would then push what our understanding is of the system. And so with that, I want to very briefly in one slide talk about another topic that could be its own entire separate talk, which is system level imaging. So beyond just having these constellations of either a small number of spacecraft that might have more instrumentation and suit more tailored science, or these large constellations of more limited measurements you're taking, but spatially, you have a lot of them spread out throughout the system. You can also then start looking at, well, what can we get from remote sensing observations? And so for this, one of the really great things is it's possible to determine the full system energy and mass cycles. It allows you to get global coverage from one or a few spacecraft that can be sitting there and really look at the system as it stands. And so this is one of those areas that I feel that we as a community have had several examples of. So if you want to look at twins or image, but I would actually say that I think this is one of these areas that we should consider pushing more in the future and making sure that we don't leave this out, because I think that it has a very valuable role to play within our set of missions. And so in this, the considerations you have is that the conversions from remote sensing to physical parameters are non-trivial. It's not that easy to take these line of sight measurements, especially if you don't have all of the ancillary products you want, like what is the density everywhere, in order to then reconstruct what you have. And also, not every remote sensing instrument is going to want to have the same orbit. And so you're going to have to consider things like, if you want to have one of your instruments really far from the Earth in order to get this nice big picture of the whole system, the other one wants to focus in just on the ring current, wants to be a little bit closer in. Either you do trade-offs between those 2 instrument teams, or you need additional spacecraft to be able to put those instruments at different locations. But what we do see is that if we have all of this, especially this in conjunction with having all of our in situ assets, this really can then give us a more global perspective of the system, and be able to really look at how mass and energy really do flow throughout the magnetosphere, especially during times of different kind of driving. So where I kind of want to summarize everything is that at this point, from my standpoint, most observables in space physics have now been measured from a single point framework. With Parker Solar Probe, we've even measured the subvolcanic solar wind. There's not a lot of places we've just never measured something. But what this really allows us to do now is think, okay, so what measurements do we need with what separations at the same time? How can we really start pushing this forward? And so from my standpoint, the missing gap in understanding now falls in the need for these kind of multiple observations at relevant scales and positions. And while some of this can be done without new missions, again, I think the HSO is underutilized. I think we all need to look beyond the mission that we are tied to, and try to use all the assets we have. And there is a special issue for that. So please consider putting a paper in. But really then the path forward in my mind is going to be this, what can we do as far as miniaturization and COTS in order to enable more multi-point measurements, understanding the trade-offs we have with that. When can we get by with the degraded performance? When do we need the high-performing instrument? Small number of spacecraft constellations are going to be really critical if we want to be able to have all of the measurements we want to have that clearly you wouldn't be able to put on 30 spacecraft. You really, if you want to have every kind of measurement, you're only going to be able to put that on a limited number of spacecraft. But then really the question is, how many spacecraft do you need and with what separation and where? And then when we do want to go to these more global vantage points with these large number of spacecraft constellations, then that's great. The question is, what measurements can we give up? What measurements do we really need? Because we're going to have to make some trade-offs there. And then how are we going to get around the data visualization problem of how are we going to the point where if you have 60 measurements throughout different parts of the neosphere, how do we actually represent that in a way where we can do science with it instead of just kind of scratch our heads and get dizzy? And then how can we then fit system-wide imaging into all of this? How can we have it where we have, I mean, if you want to make the analogy to what we do in meteorology, you have all of these. We have the very large weather stations that have all of the measurements to high precision, but there's only a few of them. We have the distributed array of limited data sets throughout, both on land and in sea. And then we have space-based remote sensing that looks at this. And so really when you go to meteorology, there is a home for all of these different architectures. And so we need to find a way to start bringing all of them in a very collaborative sense into our community. And then beyond that, there's probably pathways that we haven't realized yet. I'm sure there's plenty of great ideas probably in this room that were not captured in this presentation. And really, we're not gonna know what the future is until it's no longer the future. So with that, I'll take any questions.
Yeah, thank you very much. Very interesting talk. One question you mentioned that when you have a multiple satellite, especially just in situ measurement, so you do not have a common reference, right? So it will be very hard to do cross calibration. Do you have any kind of idea or suggestion that we can improve that kind of calibration?
Yes, it is tricky. A lot of times, I mean, we kind of end up almost cutting the differences and cross-calibrating just to have everything agree. But you're right, you can have general offsets. I think there are times when you can do certain tricks, like if you go out in the solar wind for magnetometer times, you can get kind of a ground-based truth for some of your calibrations. But it is a tricky thing of how do you actually know a value is valid.
Yeah, just follow on that. Just wonder maybe we can do kind of a remote sensing combined with in situ measurement if we are looking at the same parameter. So then we can do kind of cross calibration because remote sensing can cover scale, different regions to look at a certain region.
Right, and that's a really good point because I mean, the remote sensing is going to have its own, uncertainties tied to it. But I think with having then the remote sensing being able to see multiple assets and then being able to compare all of those data together, especially if you understand where each of the biases in the measurement might point to, that might be really helpful. So I agree.
Hey, Robert, I guess
Hi.
I have a question and a comment. So first of all, this was a super amazing talk. I really enjoyed it. And I think as a community, we often talk about like, what kind of constellations do we need? But your talk actually like captured the logistics of it and what it means. And so the question is, are you going to write this up at all, do you think, in a white paper or, because I think it's so useful.
Yeah, so thank you for the compliment. I haven't thought about that. So I mean, for the mission concept that I briefly talked about, I mean, I am putting that in its white paper. But
Okay.
as far as this as a general framework, I probably should. We should probably talk about that later.
Okay.
That's a good idea, but I hadn't thought about that.
Yeah, just you went through the work of compiling this, so it'd be great if, anyways, thank you so much. And then my kind of comment is I liked the last point about using system-wide imaging. And I appreciated that slide you had. And so the comment is just, we heard like from Emma Spanswick earlier this week on her proposal of trying to upgrade the Canadian infrastructure. And so I guess this is just me saying, I think we need to try to support them if we can, so that we do have this two-dimensional framework to like put our observations within. And also that there was in our session yesterday, Martina Gulidu talked about using ENA imaging, kind of like twins, but using with like higher time resolution, better spatial resolution as another way to try to get like a two-dimensional framework within which we can put our multi-point observations. So that was like one more idea we heard this week. So thanks again.
Yeah, thank you.
So, hi, thanks for putting all this together. I like how you provided the differentiation for what the science objective is so that you can see what risk you can take on different instrumentation rather than going all out unnecessarily. So I think that's a very valid consideration. I wanted to ask, and then I wanted to bring a comment. Have you thought on all of these multiple constellations, what other technologies our community should be pushing for to make that realistic? Because, for example, I don't think that if somebody now put in 40 satellites out there, said that it's done, magically it is done, 40 satellites with instrumentations out there, are we ready to, for example, do we have the comms to get all that data down? Do we have the infrastructure to process all that data and make sense out of it? So what are the other technologies that we need to be promoting that may not be necessarily space physics technologies, but that we will need in order to actually harness this data and make use of it? So that's the question. And once you give your answer, I have a comment. Okay.
Thank you for the question. I think it's a really valid one. I agree that we do often have that bottleneck of telemetry. And so that's why, a lot of times we'll have, even with current missions, you select intervals for burst mode because you just can't downlink everything. There have been advancements. I mean, interestingly enough, Amazon is getting in the business of, if you're in low Earth orbit.
SpaceX and Starlink are doing it.
Right.
1,600 Starlink satellites.
Right. And so I know there is a trade-off for if you are, close enough to Earth, there are starting to be commercial partners you can go to for your telemetry. But especially if the further you go from Earth, that quickly you rely on the DSN, and the DSN isn't really, it's overstrained. And so it would be nice to see more investment in the DSN.
Well, not just nice. I want to stress that as a community, as you very nicely advocate for this, we should remember to advocate for the other pieces that we need to have ready for this to actually happen.
I agree.
Yeah. So in terms of a comment, I wanted to remind everybody that there is a Living with the Star Architecture Committee that is preparing a whole lot of concepts to advise as an advising report to the decadal survey. And that report includes, it has gotten input from a whole bunch of people that are even in this room. And it has mission concepts that have a lot of elements of what you described as well. And I think as a community, we should be aware of all these efforts, because I don't think we can advocate for them from enough venues and with enough loud voices. We just need to remember all of these voices matter.
Do you know if the Living with the Star Architecture report is including findings on the non-mission level infrastructure, like such as DSN?
Yes.
Okay.
It does.
Good.
I'm part of the committee.
Yeah, I'm glad to hear that. That's good.
Okay, is this working? Yes. So a question from online. Great video graphics showing the satellite locations. Is that available online anywhere?
Yes. Whoever is online, if they email me, I can find where I got that from and send it to you.
Hi, this is Lisa Winter from NSF. I just wanted to follow up on that. We had an ideas lab in 2019 for constellations of satellites and CubeSats. And it was a really successful program. We selected 2. And the interesting thing is we were addressing this issue of what else do you need? We had engineers, communication specialists, all in the room for this ideas workshop to come up with not just the science drivers, but also the technology that we need to support it. So it'd be great to hear from the community, particularly in white papers, to the decadal, advocating for more of this type of interdisciplinary approach. The agencies would love to hear that. I know NSF would, and NASA, I'm sure, would as well. So I'd really encourage that from the community and look at that program. And also, if you'd like to see more of that kind of thing from NSF, please send your feedback to us at NSF, because we'd love to hear that. And also on Ampere, I did have a question following up on that, because NSF supports Ampere. Mm-hmm. And I think there's a lot of potential in that commercial scientific partnership. The Air Force was looking at this as well with the CEAS instrumentation and trying to get all of the commercial satellite companies to also put on a CEAS instrument to monitor. And it would be great to see that kind of encouragement in the decade, also that kind of advocacy for working and partnering with the commercial sector. And I'd love to hear your thoughts on that as well. Thank you.
Yeah, I really like the idea of the few white papers you outlined that would be great for the community to do. I do want to say that I think that as far as the partnership with commercial vendors, as we see with Ampere, thanks to NSF, it really allowed for, I was hard pressed to think of another kind of large number scientific mission or facility that exists. And I think that, this is one of those things that it's sometimes prohibitive for us to be able to get that number of spacecraft unless there's some commercial element. Because the nice thing for Ampere is Iridium has another revenue stream. And so they can maintain these spacecraft without necessarily needing to charge everything to the science data that we're getting. And so I think that, it is a thing to be pushing forward with the understandings that, you're going to then have to work with what they're willing to compromise for. And there's going to be some information you might not be able to get, would like to get, but I think Ampere is a golden example for where that can work really well. So, yeah.
Oh, yeah. So two quick things. So the first, for the question online about those videos, those HSO videos are from, you can find those on the Goddard visualization website, actually. It would be awesome to have a version of those with all of our NSF assets as well as some other, like GOES and I know some of the other things coming out of NOAA. So it's fun to think about the HSO and think about what's not captured from that one NASA specific slide. So I think, yeah, for the Ampere type of constellation, I'm always for more types of Ampere measurements everywhere, obviously. We had the great fortune, because of the partnerships and the development work done during the original constellation, the Block 1 days, that as we moved into them replacing their satellites to the next constellation, that we were actually on the ground floor. And a lot of that was thanks in part to our support with NSF, to the lessons learned of working with industry and the particular needs that you have to understand from both sides. So I think as we're thinking of how do we have hosted payloads like that, because Ampere's not the only data stream coming off of Iridium. There are a couple other hosted payloads. Some we're allowed to talk about, some we're not. But understanding like those mechanisms and the partnerships that you have to build, and understanding that times as that hosted payload, that if they are doing spacecraft maneuvers and different kinds of operations, we are kind of second fiddle. But what I will say is I think that's been such a fruitful partnership. So that is something definitely worth exploring, but it takes a lot of groundwork before you ever see anything fly. So if you're thinking of thinking about Starlink, thinking about the OneWeb, that work needs to start like 10 years, a few years ago. But so as you're thinking about that, start making those connections now, because I think the more is even simple instrumentation that we can get on these global satellite constellations in LEO, I think the better it'll be for our science, especially as we're going after things like, can we get some like particle, measurements to get pointing flux, right? So things like that. So shameless plug for Ampere. Our next data is about to be released imminently. Look out for an announcement in the next week or two. So thank you.
Thank you for the nice talk, Robert. If I were a student, I would like to know how I can involve in these mission plannings or mission teams. So would you share some ideas how students can be involved?
Yeah, so to to a large degree, I think most of us are very friendly people. And so if you see someone talk about a mission concept that they're wanting to push forward, or you're chatting at the meeting with someone and they bring up a possible thought, just ask to be involved. Typically, there's plenty of work to be done, even if it's just, attending meetings to talk about different trade spaces. And I can't think of many people who would just put a hard no for a student wanting more involvement. But that being said, from the point of view as someone who's just finished a mission concept study, I don't necessarily know if people want to be involved. And so that's partly why, I went around doing, different seminars at universities to, at one point trying to get the idea out there. And so it's if no one says they're interested, I will not know that. So if anyone is interested in more, please talk to me offline.
Yeah, thank you for the great talk. I have just a comment regarding this problem of the data downlinking when we have 40 satellites and so forth. So for example, with the MMS, there is always this a satellite in the loop, which then, okay, now start collecting burst mode data and send it back, when something interesting is happening. So of course, now once we have and we understand more and more, what kind of, events we want, and then we can use also artificial intelligence and machine learning, because we can't have, for example, 60 scientists in the loop, looking at the data and, send it back. But we can have these kind of like algorithms within the spacecraft, and then we can, decide when to send the data back. And that's especially important now I'm working on the concept study as well for utilizing the Venus sun Lagrange points. Mm-hmm. And of course, then the spacecraft goes sometimes behind the sun for long periods of time. And then when you come closer to the Earth, that's when you have to start dumping all the data down. But then, it's also a problem, like where do you store that data? And so I think that's one thing we can already start prepare for that now. Like, how do we train, artificial intelligence to pick the data that we want?
Yeah, and that's a really good point. I know there are some groups that have been trying to work on that problem. And I know that there's been some push to move from instead of a scientist in the loop to like a scientist over the loop, where you mostly have it automated, but there's still a scientist overseeing, because sometimes the algorithm pulls out exactly the criteria you gave it and something else happens that was totally unexpected. And so you need that scientist to be able to go in and say, like, oh, actually grab that. That's really cool. But I know there is these pushes to how do you move to having it more and more automated. So that's a really good point. Thanks for bringing it up.
Okay, we've got one last question here.
Okay, thanks. Just wanted to say again, wonderful talk. I thought I certainly learned a lot. And just wanted to follow up on Katerina's comment. I think that along with the advancements in hardware and measurements, we should also be thinking about advancements in what analysis and visualization techniques, as you've alluded to. Again, following Katerina's point, I think machine learning could have a really unique part here, both in calibration. For example, we could take individual spacecraft and build dynamic spatiotemporal maps for each one individually, and then just compare them, and you can see how we intercalibrate pretty easily. Or the allowing of discovery of partial differential equations automatically with large N clusters. So all kinds of possibilities open up that we've never had access to before. The question that I had has to do with, I think something FT alluded to, academia industry partnerships. And it seems inevitable that there will have to be some kind of partnership as with Ampere, and I wanted to get your thoughts and anyone else in the room about whether we possibly are thinking about this the wrong way, where we're thinking, let's tack on to SpaceX or something else, right? But I wonder if, I think the problem there that I've heard is a lot of satellite providers are maybe a little bit hesitant to give out their positions or some of their telemetry. So perhaps another way to do it is if we're building constellations to rent out some space for industry applications. And I wonder if that might be a potential avenue that we could pursue.
I think it's a really interesting point. I think a slightly different thing is actually, so what they're kind of doing with some of the PRISM calls is for NASA is procuring these landers to go to the moon, and they basically say, if you have extra mass, it is up to you what you do with that, but we have paid for this to go. And so then it would allow for a way to have a partnership where then they can say, oh, great, we do have this extra mass capability. I'm going to now sell it to this person, or I'm going to add this instrument that I want that does communication or something. And so I think there are different ways, and maybe not us being the owners of the spacecraft and totally leasing it out, but maybe kind of saying, as long as you meet these requirements that we need for science, you have the freedom to then expand out capabilities for your own use. And that might be a third option.
I wanted to follow up with a comment. Excellent points, Jacob. But what I wanted to follow up with, a lot of the industry, they don't want to carry payloads in just 5 or 10 or 20 satellites. They want to have a contract that says 300 satellites. And that makes the cost prohibitive for NASA. Or the other limitation is that their satellite goes as a package deal. You can't change anything. You've got to fit to it. And that is limiting with the way we're used to thinking. But I think I advocate that we start thinking differently because we need to capitalize on all these opportunities. You have to fit, and you alluded to that. What kind of sensors can I use that are not perfect, but if they go into 400 satellites, maybe I'll get an extremely great benefit. So we got to think this way. And the last thing that I wanted to say is, along with what Jacob mentioned, we got to start thinking, if we're going to do all these many satellites, do you think there is a university or even a NASA center that can build 40 of something? Yes, dead quiet. No. So we've got to think of industrialization, production plans, and how we're going to partner with industry to get those built. Mm-hmm. So there is a lot of elements, and we've got to go through this. It's nobody here, I think, can promise 40 of something.
So I think we have one last question.
Yeah, okay, well.
Okay, do we have one last question?
Yeah, we have one online question from Howard Singer. So GEM deals with models. Can we continue? GEM deals with models. Models can be used to aid in constellation planning, visualization, data assimilation, etc. So what direction would you like to see GEM go in order to contribute?
So that's a really good point, because if you want to do, I mean, so there's, I actually forget what this acronym stands for, so maybe it's going to help me, but there's the Aussie framework where basically you end up flying virtual spacecraft through a model to actually simulate out what you would get. You can actually put in then, you know, degrade your data down to the point that would match the instrumentation you're flying and see, can you then back the other direction, reconstruct anything? And I think maybe one aspect then that GEM could go is if those that are constructing these models had ways that someone who wants to do mission planning could easily do an Aussie run with their model. I know some groups already do that, but I think that's the main way I could see to answer Howard's question.
Yeah, that's observing system simulation experiments.
Thank you.
We had several talks on that Wednesday at the MFD session.
Yeah.
Okay, thank you. Great discussions, but we need to continue. So I would like to invite the students to introduce our next speaker. Well, I try to change here. How do I change the?
Oh, where's the next one? Jane, I don't know what I'm doing.
Good morning, everyone. My name is Trishonda. I am a third-year grad student at the University of Texas at Arlington, and I'll be introducing our next speaker. Our next speaker is Dr. Katie Leka. Dr. Leka is a senior research scientist at West Research Associates in Boulder, Colorado. They received their bachelor's degree and Bachelor's of Science in Astronomy and Astrophysics from Yale University, their Master's in Astronomy from the University of Hawaii, and obtained their PhD from the University of Hawaii. To date, Dr. Leka has been an author on 75 refereed papers. Dr. Leka's research interests are expansive, including solar flares, solar active region structures and evolution, validation science for space weather research, spectropolarimetry, vector magnetograph instrument development, and analysis techniques. Beyond their scientific achievements, Dr. Leka is also an award-winning chocolate chef. Unfortunately, they will not be revealing their culinary secrets today. However, they will be giving a talk on a very different type of science. So today, Dr. Leka will be giving a talk on validation and evaluation of solar and heliospheric science. With that being said, let's welcome our next speaker.
Chocolate rules, right? Chocolate rules. Okay. Thank you so much for inviting me. This is my first GEM meeting. I'm a SHINE person, and I was invited to give a little bit of the SHINE perspective, especially talking about validation science. How do you know how well you're doing, how well things are working, how well your model works? And sort of like, are we there, here, there, where are we in this? And so I'd like to just touch upon a couple of things. And I know it's a different realm to the SHINE session. So I'll try to not use too much jargon, but please, if I do use a term that you're not familiar with, raise your hand. Okay, so lots of collaborators that I've been working with, but let's go. Okay, SHINE science. What is SHINE science? Well, it's the stuff that's highlighted in the yellow there. We are the solar, heliospheric, and interplanetary environment part. And as a little trivia thing, there was a SHINE meeting, I believe it was in Quebec, and it's turned out that the border control people were asking a lot of the participants, what does SHINE mean? And it really became important to know what that acronym meant. So we encompass the sun, so that's solar physics, which is really the driver of most things heliospheric, provides the boundary condition for modeling all things heliospheric. The structures and events that we talk about when we're talking about solar physics are things like coronal holes, sunspot groups, and their remnants as they evolve, irradiance variations that impacts all of geospace, solar flares, coronal mass ejections, those initiations. The challenges for the solar physics part of this are things are both spatially extended and unresolved. So we have huge variations in scale. The evolution is on really all time scales, and that is a challenge. The events are both temporally discrete and also spatially localized, but they also can be extended. So, pick your scale, and we've got it covered in solar physics. If we move into this sort of coronal heliospheric boundary, we're talking about the interface between physical regimes when you're transitioning between whether things are plasma dominated or magnetic field dominated, and also the transition between observational regimes in terms of what kind of data we can get and what kind of physics can we actually sample or get an idea about. The structures and events in that boundary area are coronal hole boundaries, the co-rotating interaction regions, acceleration of the coronal mass ejections, where they really start to impact the heliosphere. The heliospheric current sheet, where is it? How sharp is it? Which direction is it going? And also, of course, solar wind acceleration. The challenges, again, the structures are large, they're global, they can be sharp or they can be undefined in terms of their boundaries. The events can be discrete or gradual. Again, all these different kinds of timescales. And then we get into the heliosphere and interplanetary environment, where this is the regime of most Earth impacting phenomena, which until recently, we really only got to sample near the Earth. Those are the only data points that we had. The structures and events are things like the solar wind propagation, plasma turbulence. This is all the stuff that's coming at you for GEM, right? This is all the stuff that we're sending your way. The challenges, again, global structures, but global phenomena that are very structured. And again, a lot of scales to go on. One of the big challenges that we have that I don't think that you folks may appreciate completely is that all we have are photons. Our in situ measurements are really sparse, okay? All we have are the photons. We don't measure the magnetic fields on the sun. We don't. We infer them from what they're doing to the polarized light, to the light that's coming from the sun. Okay, and that is a huge, huge thing. It takes many steps for many of the things that we say we measure. It takes many steps, including modeling and a lot of assumptions to get to where we say, oh yeah, this is the density. Maybe, okay? So all we have are set photons. We don't get to go and probe the sun. So Parker Solar Probe is great, but we're still not really sticking the probe into the coronal loop quite yet. I also want to say, and I want to make clear that I'm using the word validation to mean in the evaluation of how well something is working. A lot of communities use validation or verification differently. So that's how I'm using it here. The limited in situ environment. Okay, you guys may complain about in situ measurements being sparse around the Earth. Now we're talking the whole solar system. Okay, we got like 5 measurements, right? So it's really sparse. Data are becoming available. We're also looking at, again, data sampling from other planets, but it's it's sparse. And again, sort of a come to truth moment here, Earth to scale there, and that's a solar flare image. Okay, we're talking different regimes here in terms of scales. But the events that we're trying to look at are extremely rare. They are a medium or a large flare, and you can put coronal mass ejection in there or some other storm type event, is really less than 1% of your active region or your sunspot group days type of event rate. So basically, for many of these kinds of events, if you forecast or assume that you're in a quiet type of period, you're going to be right most of the time. And that's a thing to remember. So the event rate as well for a well-observed flare, coronal mass ejection, SEP event, a particle event where you get to see everything really, really well, all your instruments are working great. Yeah, that's really rare. So how do we know what we know? Well, we've got to have this collaboration between models and observations and also the validation evaluation, because that is really, I'm not talking about like how well does my forecast work here. I'm really talking about how well it's a way to have some feedback for your models of how well are we understanding the physics, is how well can you predict, in big air quotes, a physical quantity. So for your observations, what do you need? Full accounting of uncertainties. That's rare. I'll say that. That's rare to have an absolutely full accounting of all the uncertainties in a data set. An exacting understanding of the limitations of that data. Again, oh, we're measuring the magnetic fields. Yeah, no, we're not. Okay, at least for the solar work, we're not. We are inferring, we're estimating. And also consistent data quality and an ability to provide sufficient quantity of data. And then we go to the models where we need physical or synthesized observables for direct comparisons. If someone's giving me density and I can only see white light emission, from a particular satellite or a particular instrument, we need to make sure that we know how to connect those two so that we can have quantitative comparisons. And there's a lot of steps in there. And a full accounting of the impacts of data, of assumptions and data manipulation. So this is where, in the solar field especially, I work on magnetic field measurements or inferences or the polarimetry, and then I produce this beautiful data set, and then I give it to the model. It's like, well, we can't do 1024 by 1024 by 1024, so we're going to just bin it down to like 128, cubed. I'm like, that makes me nervous. So we need to have a full understanding of really what are the impacts of doing the data manipulation to then input to the model as boundary conditions or drivers. For the validation and evaluation, you need quantitative metrics. Numbers, graphical tools, they need to be informative and intuitive. That's important. So you need to be able to look at a number and say, yeah, that's good. Okay, I got it. Or yeah, we got some work to do. And and also to recognize that one size does not fit all. So things that we use validation, or some of the sort of aspects that we use, things like time series data, spatial maps. You know, when you're trying to compare two things, the simplest is the by eye, right? Chi by eye, or how well does this work? Yeah, looks good, looks good. Okay, now the next simplest maybe correlation coefficients. Mean squared error is a very popular one. Limited information, and also you need to be careful again of by eye. But you know, they look pretty good. Looks kind of matches. There's also dichotomous or yes, no event type of evaluations. Did it rain? Did it erupt? Yes, no. These are often provided by taking a continuous data set, setting a threshold and say, okay, did we get to a particular TEC above a certain amount or something like that. So forecast in these contexts can be really loosely interpreted. So the simplest, for example, is just how well did we do? How many did we get right out of the whole thing? So we often will construct these things called contingency tables or truth tables or confuser tables. Oh, we have a how many did I get right? How many of the different errors did I have? And then how many did we get completely wrong? Okay, so a cautionary note from a wonderful textbook. Beware of improvements in your metrics that are in fact due to refinements like a moving target, okay? Or the fact that your data quality that you're comparing to just got better. So for example, on the bottom is a very, very early global map of the world from back in the 1500s. And on the top is, you know, imaging that we have. So if we wanted to ask where a certain feature was and the answer changes, it's because the data got better that you're comparing to. So goodness like beauty can be in the eye, goodness of your model or goodness of the evaluation, like beauty can be in the eye of the beholder and has many facets. So I'm going to do a couple of case studies just to give you an idea of the kinds of challenges in some topics in Shine Science. And this is a very busy slide, but we'll step through it a little bit. Case study is modeling the solar wind and the interplanetary BZ. And there's a lot of different steps there. So let's unpack this just a little bit. So the input are usually photospheric maps of the magnetic field from the sun. Values there are the value that you put into your model, you know, what's the magnetic field? Some people often ask me, oh, Katie, what's the value of the magnetic field in that sunspot right there, right there? And I'm like, well, what do you want it to be? Because depending on how we manipulate the data and how we do the inversions and how I interpret it, that could be, you know, what would you like it to be? You know, and we try to do it as carefully and exactly as we can, but there are limitations and also what the models can accept. There are limited options for direct validation, even at that beginning step. Again, what's the strength of the magnetic field in that sunspot? How to actually verify that our models that we use to interpret and get that answer just to begin with is very difficult. Then we want to actually construct the full sun, right? We don't just want the facing side, because it turns out if you have your model and you're assuming something, but you plunk an active region on the side that you can't see, it impacts the entire model of the heliosphere. So we don't get to see the polar fields very much, and they're very impactful. So how do we model that? How do we estimate that? The options for the non-visible side of the sun are either kind of whatever I saw about a month ago or a model, lots of uncertainties. So this is where you can start to see the uncertainties building up. And for any particular pixel, what's the error bar? It gets really, really difficult to say. Okay, and then you take that and you do some physical modeling, which I'm going to call magic, but using everything from very simple, just almost mathematical expressions to full MHD models to get to that coronal heliospheric boundary. It's getting more realistic. These models are getting more realistic, but there's almost no option for direct validation, even at that step. So this is the first, you know, we've got started the boundary, big error bars, we don't know. Next. So we often have an assumed correlation between physical quantities and observable quantities, or we'll try to do that relation. So for example, here you can see field lines. Those lines are from a model tracing out the magnetic fields, and then you have a white light image from an eclipse. And we're hoping that those two, we assume that those two are going to have some correlation. And obviously there's more than just an assumption there. There's a lot of background to that as well. However, it has huge assumptions in there. It's quite a challenge. So I don't know if this is going to play. Whoops. Anyway, so the more physics, let's see. Okay, nope, I don't know if that's playing or not. Okay, well, it's okay. Okay, there we go. So you go from having that boundary of into the heliosphere to doing the heliospheric modeling. Again, a lot of these are MHD models. They're getting more and more sophisticated, and they're starting to include more physics. And then we have these point sources of in situ measurements that maybe we can compare to. And there are a few of them. And so, for example, on this bottom right-hand panel, you have a comparison of data from the Omni spacecraft to one of the heliospheric global models. And as you increase the physics, it increases the computation time. So it's an interesting kind of balance between the detail that you can get in these models, the scale, the structure that your computing resources can actually accommodate, and the amount of physics that you want to put in to get the answer right. But the in situ options for validation then are really sparse spatially, really sparse temporally. They may have a good temporal sampling at one spot, but that isn't going to maybe last for more than a few years, or it's going to sample just a few of the kinds of events that you want to get. And they're also rarely identical, as was alluded to before. So you have these comparisons, and it's like, is it good? Is it not? Are we working? Okay. And then you have things like Parker Solar Probe data coming in, much higher resolution, much higher, seeing these structures that are just wildly temporally varying. And so this is now the data has shifted, the goalposts have shifted. So in this case study, you have a gazillion steps from start to finish. And so a lot of times there have been like, well, what happens if we change the boundary? How does that change our evaluation of the solar wind? Where do we start in terms of understanding this chain of event? Each step introduces uncertainty. And I think this is something that really, really needs to be taken to heart. Each step has got to be validated and evaluated. And most steps, we can't do that directly. So coronal holes in the boundaries. This is kind of an interesting one where, again, we have a really good idea that coronal holes impact the co-rotating regions. For example, the high-speed solar wind streams are going to give us changes in the Earth, in the global environment. So we want to know where the coronal holes are. How do you identify a coronal hole? Oh, that's easy. It's right, right? Okay, there it is. That's about it. Okay. We know that they have dominant Doppler blue ships. We know there's outflow happening in the coronal holes. We know that they have lower densities and inferred open magnetic flux. And sometimes it's easy by eye. Okay. Unfortunately, they're also sometimes obscured. And sometimes it's actually kind of a different structure that's kind of making it dark instead of a coronal hole. So for example, here's three instances. On the left-hand side, you have a AIA image from 103 angstroms. And on the right-hand side, you actually have helium 10830, which the equivalent width. So that line actually looks at the temperatures and the outflows in the middle chromosphere and high chromosphere. That's really where these coronal holes are starting to do their stuff, okay? Yay, we've got a good coronal hole. It's basically on the right-hand side, whether it's bright is where you're probably going to have coronal hole type material, at least some diagnostic indicating that you're in the coronal hole. B turns out to be a filament channel. It's not actually a coronal hole. And C, there is something there, but it's obscured. So a lot of the automatic or even human eye contouring will not find it. So, and the other a challenge is that wonderful diagnostic, the helium 10-830 is these days is almost never available. So there we go. So sorry, I don't know what's clicking. Validation challenges, limited answer data, right? So what's happening, there's a lot of work being done to like have machine learning, identify coronal holes. You've got to train it on something and you've got to validate it on something. And you know what we're doing? We're validating it on someone else's idea of what a coronal hole is and not a physical quantity. So it's kind of a validation by consensus or validation by committee of humans. And this is a little bit away from the physics of what the coronal hole is. And so this is an interesting challenge of how do we validate this, or how do we urge or some creative thought on how to actually not be just kind of coming to a consensus on the most obvious structures. On the right-hand side is comparisons from 6 different methodologies. And if you look closely, some of them work, some of them agree. I won't say work, some of them agree and some of them don't. Okay, so those were all thinking about spatial and time series types of events. There's also dichotomous metrics, and this is something that I work on a little bit, which is solar flare prediction, where you have the general steps of taking solar data, solar imaging, a lot of historical stuff, coming up with some rules, and then doing a probability prediction of an event. And so you have to define what your event is, and sampling a large set of events and non-events. Warning, here case studies can be misleading. So like I mentioned before, on some of these dichotomous type things, you've got metrics such as accuracy. How many did we get right over how many total? Pros, easy to compute, right? Cons is something called the Finley affair. Accuracy is really easy to get a very high number that is completely misleading, and it's actually worse. So if you, for example, have, tornadoes is what the Finley affair was about. Tornadoes only happen in this particular area 5% of the time, if you're, however your event definition. So if you predict that there's never going to be a tornado, you're going to get it right 95% of the time. And if you use a really sophisticated model and your model predicts with an accuracy of 94%, it still sounds great, right? That's an A score, okay? But it's worse than if you actually said there was never going to happen. So this is one thing that we get into quite a bit with the rare events on the sun, is how do you show that you're doing better than if you did one of the, I don't know anything. Okay, or climatology. What's happened over the last 20 years? If I just use that as a prediction, how well can I do any better than that? There's also something called this true skill statistic, which is one of these measures that should be able to tell you how much better you're doing than default, but it's very popular. It's less sensitive to this changes in like how rare is your rare event. But you can also get very impressive looking scores by not kind of telling all the things. There's something called a probability threshold, which is what's the probability that something's going to happen? 50%, right? 50% would be a default 50 yes or no. Like if it's over 50%, I'll forecast a yes. Depending on how you set that threshold impacts this score that is very popular. Okay, so it turns out, and this is some work I did, to evaluate things for dichotomous events, it's really, really important to use a number of different metrics, because every metric, and I'm not going to go through all of these, but every metric that you use tells you something different. It asks a slightly different question. It normalizes differently. So the upshot is, for full evaluation of any system, and I'm going to put this for any system, more than one metric is usually advantageous. Okay, so those were dichotomous, those are scores. There are different skill scores and evaluation scores there. There is, for example, the percentage correct, you can see is over the left-hand side, it's all up near 1, right? So it's like, we're doing great. But things like some of those middle scores, which are scoring closer to 0, those are ones where they use a reference, say how much better are we than a reference like climatology. And you can do this like, comparing 2 different models to each other. And so these are like single number type things, but you can also use, and it's very popular to use and very helpful, I think, to use graphical representations of performance. On the left-hand side is something called a reliability diagram, where you do the forecast probability versus the observed frequency. And you can look at where it's perfect, and you can, where is just climatology, where would I be getting no skill above something else. On the right-hand side is something called the receiver operating characteristic curve, or ROC, and there's also reliability anyway, it goes by different names, but they all have ROC. So we call them the ROC curves, and we're all safe. And essentially that's taking the different components that went into this true skill statistic and looking at how they vary with that probability threshold change. And again, how the curves, how things perform on these curves can be a really nice way to intuitively get information about how a system is performing. And so this confusogram is all of these operational flare forecasting methodologies put onto these kinds of graphs. On the left-hand side are the reliability plots, and on the right-hand side are these ROC curves for 19 different methods. And you can start to see some trends. For example, on the reliability plots, the orange circles are all above that X equals Y line, and the green squares are down below it. So we've got an over forecasting or under forecasting. It's very intuitive, very informative. It's easy to see. On the right-hand side, you can a perfect reliability plot, or a ROC plot, kind of goes up from 0, 0 to 0, 1, and then over to 1, 1. And you can see the purple diamonds, I guess those are, is closer to that than the green. So very easy to see the distributions. I do want to have a shout out to the CCMC, the Community Coordinated Modeling Center. They are starting to do a lot of efforts in validation. I'm not going to go through this, but these are some scoreboards here, or some examples here. They're doing a lot of work, but I'm not going to go through too much here. This is one snapshot from a flare forecasting scoreboard, and then a CME arrival scoreboard. But one of the things you can see here is there's not, it's a day-by-day kind of yes-no probability from different groups. It's not a summary of how well groups are working over like the last couple of years, for example. So validation, evaluation, effort, and payoff. This is something that just came to me in a dream, I guess. I don't know. On the left-hand side is, on the x-axis here is time on the project, the time that you're working on your project, and you've had this model, you've been developing this model since you were a grad student, and now you're a professor emeritus, and you've been working on it your entire life. Okay, well, on the left-hand side of the y-axis, the confidence you have in your model, or that everybody else has in your model, right? And the time of the project. You start out, my model's great. It's new, it's wonderful. It's got all the best physics. It's wonderful. Let's validate. And then you're like, yeah, geez. You start to do this and you're like, oh my gosh, nothing matches, right? And then you get to this like, oh my God, my model stinks. But then as you become more familiar with it and you work more with it and you understand how the validation can help you improve your model, then it's like, okay, I get it. And you start to have more confidence. Everybody else has more confidence as well. The effort that you spent on the validation on the right-hand side, but anyway, at the beginning of the project, yeah, we said we were going to validate. We'll do it at some point. Yep, okay. And then you start to do it and you're like, oh my gosh, okay, we've got to learn about validation metrics, skill scores, data. How do I incorporate the data? How do I match the apples and apples? And then you get to like, okay, I get it. You're working really, really hard and you're looking and you don't understand anything. Why is this happening? How is this happening? But then you start to get it. And then you're like, okay, I get this. I'm getting confidence in my model because these are about the same, time scales, right? And then you start to say, hey, you know what? I really want to understand why my model does this, or how models behave in a certain way, or according to a certain change that no one's ever had metrics before to explain that, or to measure that, or to evaluate that particular question. No one's done this. I get to make my own metric. And if you think through making through new metrics, and you think through that really carefully, then the community can start to adopt them. And that's pretty cool. But coming up with new metrics takes a lot of work, but it's really fulfilling. Okay, so new metrics. This is just a couple of examples of some of the things that are happening in Shine Science in terms of developing new metrics and new evaluation. One is in terms of solar flares, understanding, forecasting, big air quotes, understanding what makes the first flare. When a new sunspot group emerges and it starts to evolve, and then you start to get that first flare. And that actually catches most operational flare forecasting systems asleep. And it is a big thing where you miss. So on the bottom, on the right-hand side, you can see the evolution of some of the GOES soft X-rays. And on the bottom is sort of what happens with the forecast. And that first one, which is red, is a miss. It's the first flare and nobody was ready for it. And the same thing is also active regions will evolve and then decay. And at some point they kind of stop doing the big flares and the big CMEs. But the forecasting system is like, okay, well, whatever happened yesterday, that's what we're going to forecast for tomorrow. And then you get a false alarm. So we actually came up with a new evaluation metric to look at 2-day paired forecasts and look at whether you had, as the flare productivity was changing. So if you had no flare on day 1, but then you had a flare on day 2, or if you had 2 flares back to back or something like that. And we came up with these radar plots where, like, and I won't go through this completely, but you can very easily graphically see if you're doing things perfectly or if you're always over forecasting or always under forecasting, just by which sectors were being filled in. And so, for example, this is now, again, those 19 forecasting methods. And you can just see, like, the 2 that I highlighted on the top right there, that they look different. Okay, and so you can go back to the key and see, okay, this one's always over forecaster. This one's actually getting better than the other one in this particular definition. So the magnitude indicates the relative frequency that you got right. The sectors indicate patterns of successes and failures. And you can just very quickly say, I want to see how a particular method worked in this regime, and you can pick it out. Solar wind and BZ, there's a couple things that are happening. One is the WSA performance metric H, which I won't go into too much detail here. The paper is cited at the end. But essentially, sometimes when you're looking at the solar wind prediction, you can get a good answer for the wrong reason. You can kind of just, like, everything adds together in the right way or the wrong way, depending on how you want to say it. And so this metric actually combines the polarity of the magnetic field that is being predicted with the solar wind speed. And so you get one number that really can tell how things are working on both of those really critical regimes. The pros is this one metric. The cons is it's not normalized right now as to be intuitive. It's just sort of higher is better type of thing. And so I think there could be work. Again, this is in how do you create metrics or evaluation protocols so that they're intuitive and informative. And having things normalized where, like, 0 is and 1 is great and minus infinity is, like, really bad. That's easy. It's easy to understand intuitively. There's also something called dynamic time warping, which is starting to be applied. And this is great because it addresses, like, an unfair penalty that models have. If you get, like, the event, but you got it kind of wrong in time, or maybe you had the timing perfectly in the time series, but you didn't quite get the magnitude right. And it evaluates those 2 aspects so that you don't get penalized. That top right plot with the horizontal line, where you're looking at data and modeling that if you just predict that red line consistent wind speed, you actually get a better mean squared error than the one where the model looks actually pretty good, but it's shifted. And so that's unfair, right? Because you actually got the event. It's just kind of not quite right in time. So it provides dynamic time warping measures both. It says how off you were or how well you did in both of those dimensions. So it's really a great opportunity for a more fair evaluation of some of these kinds of time series. The cons is that it has a lot of restrictions to apply it correctly. It has a lot of restrictions on how the time series data behave. So there's a little bit of a caveat there, but that's okay. Okay, so to summarize, validation and efforts in SHINE science. Are we here? Are we there? Where are we? I think we've got a lot of work to do, but I think it's exciting. I don't really want to be the one telling people, oh, your model didn't work. But I think we can all learn from that, because if you have the metrics, especially if you have informative metrics of different that ask very specific questions and address those, then you can learn. You can learn what the bias is in your model, or what the bias is in the data, or what the uncertainties are, or where maybe we've got some missing physics. There's your new proposal, right? I can show it with this metric. So SHINE science, we are challenged by sparse data. Yeah, I think, I don't know if we're going to have a competition on who's got the most sparse data, but you know, we're we also have the challenge of it's almost all remotely sensed, and that's really tough. Data errors and uncertainties are underreported and underused. Don't be afraid of your error bars. They're your friends. So, and there's also an interesting way, and this is happening in some of the terrestrial sciences, of how to use fuzzy boundaries in validation science. So that again, like for example, in, I'm going to go back to solar flares, a flare that's just under that threshold, you know, is that going to be so much less geoeffective? Probably not. We need to make a fuzzy boundary. Like, did we have an event somewhere within this kind of range? And that can be extended to a lot of different science. Models also, it's not just data. Models underreport their uncertainties. If you change your boundary condition, your boundary input by a little bit, what happens to your model? Let's talk about this. How to incorporate these into validation efforts fairly. Again, you don't want to unfairly penalize models, but you really need to understand how sensitive they are to the uncertainties in the data that are coming in to drive them. Our top needed list in SHINE science is 4π standardized boundary condition magnetic maps, so that we are all on the same playing field and agree on it. A suite of accepted time series and spatial map metrics. We actually, for some of the dichotomous type of events, there is now kind of a well-developed suite of skill scores and evaluation metrics that we're starting to know how to use. But for these spatial maps and temporal sequences, we're really not there yet. Full use of uncertainties and large sample evaluations. Case studies are informative, love them. They can also be tricky because they can give you false confidence, if you will, or also give you false sense of like, oh, I don't get it, you know, of false sense of failure. When in fact, statistically speaking, maybe you got, you know, maybe a particular model got one instance wrong, but it's actually going to get the other 399 right, you know. So let's make sure we look at all of them. And really a recognition that you've got to walk before you can run. It's often a long, very long chain of analysis between the input and the target end. And I think that SHINE's focus science, and I'm not as familiar with the GEM science, but I'm just going to project from the SHINE perspective that we could benefit from some baby steps, some kind of, let's pull back. It's not going to be sexy, and I don't know if it's going to get, you know, proposals funded, but to really be very meticulous about some of these baby steps and what our uncertainties and our understandings are. And also, I love the cross-disciplinary, and I would really enjoy chatting about some of these issues with everybody. So thank you very much.
Hi, excellent talk. Yeah, thank you for telling us that we need to take a robust approach to data model comparisons. You just made a point there at the end to watch out for case studies, but you also made the point earlier with the Findlay affair that statistics can be dominated by the quiet times and not actually highlight and accurately get the extreme events that you might actually care about. So what's a good balance between highlighting the things that are important in our analysis, but not going too far to the one-off?
Right. That's a great question. That's a really great question. And it's a balance. I think case studies, and again, it all depends on data availability as well, but case studies are crucial for that first initial exploration. And let's see, oh, this may be important, that may be important. Let's maybe want this case study versus that case study, and what were the differences, what were the similarities? And that's how you start to build the knowledge, the intuition, right? The scientific intuition of like, I think maybe I want to go down this rabbit hole. In terms of the statistical evaluations of the large sample size, especially when you have rare events, that's where your different metrics and your different evaluations statistics come in, because many of them are more or less sensitive to case imbalance. You don't have to always have exactly the same number of non-events and events type of thing. And quite honestly, large sample can also be large sample of data points or of, spatial data points or something where you expect a difference that may not be events. It could be maybe within a few case studies. I'm always going to like, can I identify I'm trying to think of an example, but a quiet or all of the sectors of the boundary between A and B, for example. So not just this point, but this point and this point and this point. So you may have a case study of data, but you can analyze it with a large sample approach. Does that make sense? Sorry. But I think that quite honestly, a lot of people look at the rare events and say, oh no, we have to do some magic to equalize these. And you don't actually. Statistically speaking, you can do things like prior probability analysis and such that should take care of that. So, yeah.
Hi, thank you for this very interesting talk. Learned so much about data validation, data model validation, and things like that. So my question is that could you comment on any efforts and challenges to validate some of these heliocentric models at other planetary systems, especially for planetary space weather?
Okay. So with validation, you need an answer. So we have a few, instruments now that can provide some answers. Some of it is even really cool remote sensing in terms of like scintillation detections. So detecting the plasma coming or the coronal mass ejection coming from the sun, it may not even be going close to where Earth is, but we can see the scintillation changing and infer some properties from that. So that would be a different line of sight type of effort. But it's hard. It's very hard. We also, for example, I'm involved with a project to look at how to provide flare forecasts for the other side of the sun where we don't have data, but we're doing some modeling and we don't have direct data, but we have data from what's called helioseismology. And it's, how do you know when you got it right? So, and that's where having more data, many times we'll hear about missions to see other parts of the solar system, but it won't be for a very long time. So this is getting where we get into the sparse temporal sampling in a slightly different way of, I'll have maybe a few years cruise to cruise time to see events that happen on the far side. But that's all there, that's all the data we're going to have to validate against. So it's very tough. I think people are thinking about it, but creativity is always welcome.
Very nice talk. In one of your slides, you showed a set of metrics and ROC curves, and you referred to 17 prediction methods for flares. But nowhere else in your talk did you raise the issue of ensemble model forecasting.
Right.
But in geospace, we're definitely headed in that direction. So what's the status of ensemble model forecasting in the SHINE community?
Very good question. Under development. So it's, and I also want to say, I don't want to pretend to know that I know everything that everybody's doing in SHINE. I must have that caveat at the beginning. So I really hope I don't completely overlook something. It's under development. It's how to do the ensemble modeling. For things like solar flare prediction, there are different approaches of, people are looking at it. Places like the operational systems, the operational forecasting centers do not do it right now. They may have a couple of different models that are running, and the forecaster in the loop, the human, might take a look and see what's happening, but there's no official ensemble modeling work being, or method that is in accepted officially. But there's a lot of research into that. In terms of things like the, there's a slide I want to show, the ensemble modeling for BZ type stuff. There we go. There are a lot of times where there are models where the boundary condition, for example, is modified, and you will get a different model. So I was part of a discussion recently of how do you define what an ensemble model means? Is it sort of a series of almost Monte Carlo experiments with your data, input data, and just running 12 different realizations or something like that? Or is it where you're trying to combine completely disparate models into one outcome? And so there is even kind of a little bit of a nomenclature understanding we need to come to terms with. But it's an active area of research. It takes a lot of, it takes a lot of work and a lot of computing power. So I think I think people are interested in it, but it hasn't been really adopted as the way to go yet. Does that help? Yeah. I was going to say, I have seen really cool things where they take like the Monte Carlo type of realizations, the multi-realization approach, and make heat maps, and that the maximum likelihood of the curves that you get from the heat maps are the final model work, and then you validate against that. I think that's pretty cool. I mean, I've seen some new work on that. So
17 different models of flare. You referred to 17 different models of flare prediction. It seems to me that that would be an ideal place to play around.
Right.
With the idea of ensemble model forecasting, weighting the different models by some factor. And, like with the hurricane prediction, they weight the different models by factors that are dependent on the conditions.
Right. Yep. Data are there. Have fun. Go for it.
Not my area.
Hi, Katie. Thank you for the fantastic talk. Just a general question with the dynamic time warping that you presented. How does that deal with persistence? Does it penalize it? Is there a way to penalize it?
I'm not sure.
Okay.
New paper, 2022. I've got a list I've got a few list of references there, and it's there. And I don't remember them commenting in the paper specifically about that as a pro-con or a pro or a con or otherwise. I think they were, in terms of persistence, Were you thinking about like in terms of returning type of structures or?
Just a model that says, you know, I've observed this now, I'm going to now predict that's what's going to be in the next time step. And so you would have a perfect offset in time continuously. Right.
If that happens, that's kind of what is shown here in that kind of middle one where you only have an offset in time. One I was talking about the limitations of this in terms of how the time series are treated. And in that middle kind of diagram, one thing that's happening is that endpoints are not matched, and the endpoints need to match, and that's where you get this kind of offset in the heat map of the minimum curve there. That blue line is kind of offset from the x equals y line. A perfect is right down the x equals y line, or x equals minus y. Sorry, in this presentation. So it's offset a little bit, and that's because there's only a time shift. Specifically. So yeah. So I think it can pick stuff like that up. Again, I think this is a great example of figure out what the question is that you're asking. Does this metric out of the box work? Do I need to modify it a little bit in order to ask exactly that question and get that piece of information? So that's a great example. Yeah.
Hi, Katie. Great talk.
This disembodied voice, yes.
And thanks for coming. And I know there's a lot of efforts that have gone into model verification, validation, and metrics within the weather community. And there's some specific resources that you can find a lot of these things. I was wondering if the SHINE community has thought about where to put some of these new metrics as they come up. Where's a great place to kind of have them listed so you can easily find and reference them. And then perhaps something that our group should think about is, since we're a resource group, trying to make sure that we are able to collect not just those from our community, but from SHINE and CDAR as well. Because I think that would be a fantastic resource, but wondering if you guys have already kind of thought about that and have a repository.
No, not that I know of. I think in the different sub-disciplines, there are groups that are working on things. So if I wanted to investigate time series, I would talk to these various folks that are working on that. There's not a central repository that I know about. I think that things are developing fast enough that it would be very interesting to think about that, or I want to say like a living reviews type of repository, because things are becoming more sophisticated. And I think as they become more sophisticated and people understand how to use them, and if we can make them easy to use, they'll be more accessible. Many of the programs now, when you get when you apply for a grant, it says, we expect you to do, validation and propose how you're going to do that. But it doesn't say, there isn't a list of these are the standardized. So it's like, okay, I'll do mean squared error. I'm like, okay, let's do the next step, but having those tools available and easy to use and easy to easy to understand, case studies, examples, Python, Jupyter notebooks, I don't know what, but where you can see how things behave. And so you can come up with your own versions that are based on something that's been tried and tested. Yeah. Good.
I think we get one last question.
Thank you, Katie. My question is for the solar and heliospheric modeling, you are dealing with mostly two-dimensional magnetograms, and you have a lot of uncertainty in the off-limb magnetograms, I think. So, and your output becomes 1D in the L1 point, perhaps, to that you quantify in the end. So this is something that, just for geospace modeling, we use those type of uncertainties. So my question is, how do we propagate those 2D uncertainties to the 1D uncertainties that we drive our models to get the truly Santoma type of modeling?
Lots of partial differentiation. No, good question. I mean, it's hard. There's actually a point that I didn't list in here, but I had it as a point to myself to make. We need the academic or researchers writ large need, and on our field, I've really benefited personally and professionally from having collaborations with statisticians. people who are trained in statistics and how to, and who can have the intuition for what's going to introduce what kind of bias or how to propagate these uncertainties or how to combine exactly that question. I mean, I can sit down and think about it, but it's always going to have a nuance. But having collaborations with statisticians, problem. Anybody want to try and outbid paying for a statistician on your small 100K research grant? Okay, it's really hard. It's really hard to find people who are interested in these kinds of collaborations and that you can get long-term, work with. It's really challenging. Not many of the statisticians are staying in academia. Or I'll say research. I work for a small research company, but it's the same type of thing. So I think that's my last plug is if we can somehow interest people who are in math departments and statistics departments to start cross-disciplinary collaborations. I think that's a really, really challenging and important thing. So thank you for the point.
Thank you. Can you stop sharing?
Yeah, this closing. This one, the PDF.
Mm-hmm. Okay, so it's time for our closing of the plenary sessions. And so I wanted to provide some statistics here. So we had again a great GEM workshop with more than 300 participants and more than 100 students. And we continue with the GEM Shine Day, not to forget tomorrow and on Sunday. And more than 150 people have signed for that. So this will be a great opportunity for exchanging ideas between GEM and Shine. We had more than 190 posters and 58% of the participants refer to them as he or him, 33% as she or her, and 4% use their name. And all tutorials and many of the presentations are available at vgem.org. So you can download them from there and view them again. So today, a reminder of some of the sessions after the concurrent sessions, we will have at 3 o'clock a SBCCI social and memorial for Sam Bingham. Also, some opportunity to collaborate after the workshop. Please use the GEM wiki. So a lot of information is available there, also from past GEM workshop and a lot of other materials. So please use it as your resource to learn, especially for the students, to learn more about what GEM is and what were the past programs, so you can think also of the future programs. And we still maintain the Slack workspace, and also the meeting organizer will be sending you email with a survey. So please participate in the survey and give us ideas how to improve the workshop. So as I mentioned, Saturday and Sunday mornings, we have the GEM Shine Days with great programs from 8:30 up to noon. And there will be a coffee break. There won't be a breakfast, so please go and get your own breakfast. But come and participate in the workshop. The moderators have prepared a great program. And if you are wondering about next workshop, we are exploring some venues in Colorado. Probably not snowmass, it's become very expensive for us. but other areas may be Boulder and surroundings. And yeah, if you have any suggestions, feel free to contact meeting organizers. And we are still working on it, so it is not finalized. When it is finalized, it will be announced again in the newsletter, in the GEM wiki. The plan is to have it back to back with CEDAR, but this is also in the works since the meeting organizers for CEDAR are changing. But that is our plan for now. And I would like to thank especially those steering committee members that are rotating off, and they had performed such an amazing job as the other steering committee members, Alison Janes, Alex Glosser, Steve Petrinek, and our student representative, Mayun Lin. So when you see them in the hallway, please thank them. We will have a call for new focus groups again through the GEM newsletter in the fall. So it is very important to sign for the GEM newsletter. And these slides are also available on PGEM, so you will have all the links there. And the guidelines are provided in the GEM bylaws, but if you have any questions, contact any member of the steering committee. And a big thank you to our wonderful and amazing support team, Tony Roger, Jing Liao, who is helping Chris Muikis with the organization of the meeting, Greta Gabua, Andy Dove, Katie Whitman, and Umbe Kanto. So thank you. And we should not forget to thank also our student moderators who have helped get a great plenary focus group session and discussions.
Slides are just for student reps. You judge it first.
So we will first announce the student winners of the poster presentation competition. And before that, I want to thank the judges because this year we migrate everything to online. And some judges, they are still get used to it, but they all like very helpful, typing the comments in very detail on the laptop and also on their mobile device. So I'm very appreciated. We have 72 judges this year to judge 96 posters. And we want to announce our student winners. And this year, each of the winner will get $100 gift card. And we also have a colorful certificate, and that's just to congratulate all the winners. So you want to announce it?
So as I read your name, if you're here, please come up and just stay for the remainder so we can get a picture at the end. So I'm going to go through all the different research groups. For the MI coupling group, our winner for this category is Riley Ann Reed. Yes, congratulations. If you want to come up here, we'll get a picture with everybody right at the end. So thank you. And then for the global system modeling category, we have Timothy Keebler. Timothy? Maybe not, okay. For the solar wind magnetospheric interaction, Sophie Marie Graff. New papers. Congratulations. For the magnetotail and plasma sheet category, Joel Tibbetts. And for our final category, we actually had a two-way tie. So we have two winners for this category. So we have Colin William Wilkins. I guess he's not here. And then we have Myung Jun Kim. We've got two, so they're missing, I guess. So we'll just thank all of our winners again. Thank you. Thank you, Shinji. Awesome. Thank you so much, guys. Okay, now comes the announcement of our next student representative elect. And first, I just want to say just a very quick word about Mayun, and I'm going to miss her so much. And I just wanted to say thank you for everything. She's such a hard worker, just very dedicated, and she has very big shoes to fill this year. But I am confident that our candidate will be able to help us continue the great work we've done. So our junior, thank you, yes, thank you, Mayun. So our junior student representative for 2023 and 2024 is Shinju Chen. So Shinju Chen is at the University of Illinois at Urbana-Champaign and will be for the next 2 years. And I want to thank our other candidates as well, Hector Salinas and Dominique Stumbaugh. Thank you for running. It's always good to have very good candidates, and it's good when it's a hard race. So thank you so much, everybody. And that's all. Shinju, let's go.
So do any of the focus group session organizers would like to come up and say some, or any other announcements for tomorrow also, if somebody wants to share about the GEM Shine Days?
All right, hello, Friday morning science enthusiasts. Your tenacity will be rewarded in the next session at 10:30 in the Stingray room. The dipolarization group throughout our tenure has looked at mesoscale phenomena like injections and currents and flux transport and how that contributes to the global response of the system, especially in the near Earth transition region, which is the new focus group this year that we will be combining with during this session. So we're very excited to work with them, and we invite you to come hear some exciting talks. Thank you.
And in this room, right after at 10:30, there will be a session on collisionless shocks. And if you're interested in every process there is in plasmas, they happen at or near shocks or indirectly or directly because of shocks. And if you're also really enthusiastic about shocks, we have a shock session tomorrow in the joint Shine GEM session at 10:30 to noon. So show up for that too, right? Thank you.
Hi, everyone. The concurrent session 2 between GIC focus group and the IE-MIT focus group will be at Bluefin Room at 1:30 to 3 p.m.
Good morning. We'd like to invite you to our joint session, Interference Space Asymmetry and Geomagnetic Induced Current, GIC session at 10:30 in the Bluefin Room to discuss how space weather can be viewed in the context of intrinsic asymmetry. So please come. Thank you.
I'll try and do my best enthusiastic Christine Gabriel's impression. If you are into machine learning, there's a session at 1:30 till 3. We'll have a industry academia mixer, so you'll hear from students who have gone on to industry and their experiences, and actually some have come back. So we'll hear about that. We'll have a mixer between ourselves and a couple of talks, I believe. So that'll be in the Stingray room at 1:30 till 3.
Hi, everyone. So yes, so now for all of those who are staying through the weekend. So as Vanya had mentioned, we have 2 half days, one at 8, starting 8:30 to 10 for the first sessions on Saturday and Sunday, and then 10:30 to noon for the second sessions in this room. So for Sunday morning, please come to the 8:30 a.m. session. That is where we'll be talking about trying to understand the different solar wind populations and how that impacts magnetospheric response, and really diving it for be a 2-part session. The first part will be a couple of scene setting talks, kind of trying to make that connection from the solar corona, how that propagates the solar wind, and then some impacts that we've seen over that for the magnetospheric response in its variety of forms. After that, that's going to open up into discussion, because really the question is, we've been asking this question for a long time. So where do we go from here, and how do we make those meaningful steps forward in understanding and eventually maybe fully understanding how we can assess storm time impacts and other types of when we have these variable solar wind driving conditions. So hope to see you guys here on Sunday morning. Thank you.
And for the joint GEM Shine, don't forget to come Saturday also at 8:30 in this room. Thanks.
One more thing, we have a GEM and Shine student joint event tomorrow at 6 p.m. If you are a GEM student or you're a Shine student right now, you can bring your board game or anything you want to share with the student peers. Tomorrow evening, 6 p.m. See you there. Stingray, sorry.
Okay, thank you all. Well, I think it's time for a brief coffee break now.
So this one's currently on the plenary, so I have to sign out and sign. Okay. Hey, Okay. I don't speak Windows, so I don't know. Yeah. Do what you do. How do you log out of this Zoom and log into the PowerShop Zoom?
Wait, so I need to exit and minimize.
Leave.
Just leave it. Today's in this room, it's all your session. Right?
Yeah.
Yeah, so you don't do Zoom.
So are we done? We need to stop.
No, you have to, this is the plenary Zoom, so you have to leave the Zoom and,
okay.
and log into the PowerShop one.
Okay.
Now, how to find the PowerShop? Go to the Chrome, I guess.
Yeah.
Zoom links.
Wait, I have a question. I saw you don't do Zoom in your PowerShop.
Yeah, we do.
You do?
Yeah.
BSH, I received the text message from Chris say you don't do Zoom. Okay, you do Zoom.
Yeah.
All right, just hold a second.
Yeah, we can hit on the same one. I think that's the right.
Open Zoom.
Yeah.
Uh-oh.
I guess I'll get.
Yeah, I initially told Chris no, but then I told it. Then once we were told that we were using everything from one computer, I changed.
Okay.
So.
All right. I didn't know, so I changed it.
No worries.
Set up again. All right. Current session.
Don't we want to be able to allow screen sharing or?
Everything's gonna be fine.
Okay.
Okay. Come on. Okay. And all right. Just wait a second.
Right.
Yeah.
I assume we're going to be recording once people start presenting, right? Or do y'all know? I guess it's your call.
I don't know. Have they been recording in other sessions?
I've seen it in others, but it's been like intermittent.
Where are they going to put the recordings then?
I guess I don't really know.
All right. So, do one of you want to be at the back checking for the?
I'll handle that.
Okay.
And then next session we'll swap.
Okay. And I have the other focus group members here. And so Katie's here. I haven't seen Lee Chen, but Ivan Vasco's here. I know he is because he's giving a talk. So, so he can help out as well. And I do this stuff really informally. I don't like the pomp and circumstance nonsense. So it's more, my intent and goal is that there's a lot of discussion and a lot of back and forth, not just AGU talk. So we have a lot of people speaking, but at the same time, I prefer to have a lot of discussion. Yeah. So, and also just like informal, like, all right, next up is so-and-so, here we go. Not like they're from so-and-so, they have this accolades and yeah.
I don't remember. Do you have an idea how much time you want per talk? I'll keep a timer in the back and I'll warn over my.
It's 7 minutes talking, 3 minutes questions is the ideal. Okay. Whether or not anyone actually adheres to that is another question, but
I'll give 2 minutes in the mornings.
Okay, cool.
You can share screen now.
Can remote participants share as well?
Remote participant, can you share as well?
Because
Yeah.
there's people that are logging in remotely that'll be.
Yes,
Okay.
you need to.
Okay.
You just need to allow them to share. You know, there's a saying of.
One participant. Oh, yeah, go
Yeah.
ahead. Yeah, the advanced.
All participants.
All participants. Yeah.
Yeah. So, who can start sharing when someone else sharing the host dummy?
Yeah. Yeah. You don't
Yeah,
want to change that so
yeah.
that people steal it.
Okay. Do not join the audio. We're
Yeah.
gonna join the audio on the back. Every song went through the back.
Oh, yeah.
You can start a video, but it's up to you. If you don't want to start
Yeah,
the video.
don't start video. That's just waste bandwidth. The Wi-Fi here isn't strong enough to do that. It's not.
You know our weakness. I know.
Yeah.
I know.
Well, it's typical of any hotel.